Artificial atoms is the name we give to certain man-made nanostructures that emulate the behavior of real atoms, but give us the flexibility to design them for specific purposes. Real atoms are the fundamental building block of all the objects around us, and in the most simple version that many people may have in their mind, they're constituted of a positive charge in the nucleus surrounded by negative charges, which are the electrons that orbit around the nucleus, a bit like the moon around the Earth, right? Now, this is in fact a wrong picture. That's not the way atoms work because of quantum mechanics, because particles are also waves. And so the electrons that orbit around the nucleus, in fact, do not orbit like the moon around the Earth, but they have to orbit in some very well-defined trajectories to satisfy the requirement that the wave associated with the electron fits into the certain space that's allowed to it. So to this electron orbiting around the nucleus is associated a wave, and you need to ensure that there is an integer number of wavelengths, of half wavelengths, in the trajectory of the electron. A perhaps better way to visualize that is to think of the nucleus of the atom, the positive charge of the atom, as creating an attractive potential, a binding potential for the negative charge of the electrons. And then inside of this potential energy, the electron can live, but again, because it's also a wave, it also has to satisfy the condition that it needs to fit in the space that's available to it. So what we find is that the electron can only have a very well-defined set of energy levels that is determined by the wavelength associated with the mass of the electron. This is a little bit like what happens in musical instruments. If you take the strings of a guitar, the string is attached at two ends, and when you pick the string, you don't get just any random noise. You get a note. And that note contains only a certain frequency, because there is a fundamental mode of vibration of the guitar string, or it can contain some higher harmonics. That's when the string does an entire wavelength within the anchoring points, and so on. So the same thing happens here with the electrons bound to the atom. Now, the interesting thing is to wonder what is it that happens when an electron changes from one stable state to another. So when it changes from having half a wavelength to having a full wavelength between the atoms. What has to happen is that energy is given to it. And then the energy can be given back in the form of a quantum of energy or light, of electromagnetic field. This is very commonly used in lighting, literally. Some of you might have seen those beautiful soft yellow lights that you see on street illumination or parks or parking lots. Those are sodium lamps. Sodium is one of the elements of the periodic table, is an atom that has some specific energy levels such that when you excite a vapor of sodium atoms, then this extra energy you provided to the sodium atom is given away in the form of a quantum of light that is yellow. This is very nice, but what if you want to make a different color? Well, sodium will only give you yellow light. What if you want red or blue or green? Here is where modern technology comes to help us. We are now able to produce very small structures that confine electrons in such a way that the electrons will have some very well-defined energies inside of these artificial atoms. That's why we call them that way. They behave like atoms, but their energy levels are designed by us as engineers and scientists. And so we can make these artificial atoms to make green light, blue light, red light, whatever we like. And in fact, if you go and buy the latest model flat screen TV you can find in the shop, it will contain quantum dot technology. Quantum dot is another name that is given to these artificial atoms. These man-made structures have the ability to create light with a very well-defined color that can be used, for example, in flat-screen TVs. If you have a confining potential like this, like a parabola, then all these energy levels are equispaced. But the lowest energy level, in fact, does not have zero energy, is not just at the bottom of the parabola. This residual energy is called the zero-point energy, and is again a purely quantum phenomenon that has a plethora of very interesting applications, but we're going to talk about that another time.